Hello, and welcome to this session. LO2, Understanding the Principles and Applications of Electrochemistry. Have you ever wondered how electrochemical cells function? In this session, we will explore key concepts such as atomic structure, electronegativity, and redox reactions, and examine how these principles are applied in analytical techniques and real-world contexts. Atoms consist of protons, neutrons, and electrons. Protons and neutrons reside in the nucleus, while electrons orbit in shells. The atomic number equals the number of protons. Isotopes have the same element but different neutron counts. Understanding orbitals and subshells is crucial for comprehending atomic behavior. Electronegativity is an atom's ability to attract electrons in a bond. A small difference leads to covalent bonds, while a large one results in ionic bonds. Across a period, electronegativity increases due to stronger nuclear charge. Down a group, it decreases due to electron shielding. These trends are pivotal for predicting bond types. Redox reactions involve electron transfer between substances. Oxidation is the loss of electrons, while reduction is the gain. Oxidation states help assign numbers to elements in compounds. Half equations show oxidation and reduction separately. Combining them forms a balanced redox equation. Electrochemical cells generate electricity through redox reactions. Each half cell has a standard electrode potential measured against hydrogen. EMF is calculated by subtracting the oxidation potential from the reduction potential. Building cells helps measure EMF and compare theoretical values. Discrepancies may arise due to non-standard conditions. Electrochemical techniques like potentiometry and amperometry are essential in analysis. Potentiometry measures voltage to determine concentrations, used in pH meters. Amperometry measures current for concentration analysis, useful in glucose sensors. Conductometry assesses ionic content through conductivity. Coulometry quantifies substances by measuring total charge. Electrochemistry finds applications in various fields. Batteries and energy storage rely on electrochemical reactions. Corrosion prevention uses electrochemical principles to protect materials. Clinical analysis employs electrochemical techniques for precise measurements. Industrial processes benefit from efficient electrochemical methods. Electronegativity predicts behavior in wet cells with different metal electrodes. Metals with low electronegativity lose electrons easily, forming positive ions. High electronegativity metals resist electron loss, being less reactive. In a wet cell, the anode undergoes oxidation, while the cathode undergoes reduction. Electron flow generates an electric current. A wet cell consists of two metal electrodes and an electrolyte solution. The anode, with lower electronegativity, loses electrons and oxidizes. The cathode, with higher electronegativity, gains electrons and reduces. Electrons flow from anode to cathode, generating current. The voltage depends on the electronegativity difference. Electronegativity helps predict electron flow direction. Electrons move from metals, losing electrons easily to those attracting them strongly. The anode is where oxidation occurs, and the cathode is where reduction happens. A larger difference in electronegativity results in higher voltage. In a ZN, Cu cell, zinc oxidizes and copper reduces. Electronegativity dictates electron attraction strength. In wet cells, differences drive electron transfer between metals. The anode loses electrons, while the cathode gains, forming a current. This process is fundamental to understanding electrochemical cells. Voltage generation relies on the electronegativity difference between electrodes. Electrode reactions are based on redox processes. Oxidation occurs at the anode, while reduction happens at the cathode. Electrons flow from anode to cathode, generating electricity. Half equations represent individual electrode reactions. Combining them provides the full, balanced redox equation. At the anode, oxidation involves electron loss. The metal forms positive ions entering the solution. For example, zinc oxidizes to form zinc ions and electrons. This process makes zinc the reducing agent. Understanding anode reactions is key to grasping electrochemical processes. At the cathode, reduction involves electron gain. Species accept electrons, reducing to a neutral state. Copper ions, for example, reduce to form copper metal. This makes copper the oxidizing agent. Cathode reactions complete the redox process in cells. Electrons flow from anode to cathode through an external circuit. This flow generates an electric current. Half equations illustrate the electron transfer at each electrode. Combining them gives the overall redox equation. Electron flow is essential for understanding electrochemical cell functionality. Redox reactions involve electron transfer between substances. Oxidation occurs at the anode, reduction at the cathode. Electrons flow through the circuit, generating electricity. Understanding redox is crucial for electrochemical cell design. These reactions drive energy production in cells. Potentiometry measures voltage between electrodes without current flow. It's used for pH measurement and ion-selective electrodes. Its strengths include high accuracy and non-destructive analysis. Limitations involve interference from similar ions. Potentiometry is a reliable choice for routine clinical measurements. Amperometry measures current from oxidation or reduction at an electrode. It's used in glucose and oxygen sensors. The technique is sensitive and suitable for real-time monitoring. However, it requires controlled conditions to avoid interference. Amperometry is ideal for continuous clinical monitoring. Conductometry measures a solution's electrical conductivity. It estimates total ionic content in fluids. The method is simple and quick, but lacks specificity. It's useful for general assessments of electrolyte balance. Conductometry doesn't identify individual ions, limiting detailed analysis. Coulometry measures total charge passed during a reaction. It's directly related to the amount of substance present. This technique is very accurate for quantitative analysis. However, it involves complex instrumentation and slower processes. Coulometry is best for precise ion quantification. Potentiometry is simple and reliable for ion measurements. Amperometry excels in continuous monitoring applications. Conductometry offers quick assessments but lacks specificity. Coulometry provides precise results but is complex. Each technique serves a unique role in clinical analysis. Electrochemistry principles drive diverse applications, from cells to clinical analysis. Understanding atomic structure, electronegativity, and redox is fundamental. Electrochemical techniques offer varied solutions for analytical challenges. Each method has strengths and limitations tailored to specific needs. These insights empower effective use of electrochemistry in practice. If anything is unclear or you would like more information, please contact us on WhatsApp at 0748 4361 688. We appreciate your attention and hope to see you next time.